Hi, my name is Itai Seggev. I work for Wolfram Research, and my talk is called Version 12 Enhancements for the Pre-College Classroom, in which I'll be talking about enhancements for both pre-college and college-level math classes that have been made in functionality, usability, and documentation for version 12. Okay, well, welcome everyone. I'll be talking about version 12 enhancements for the pre-college and college classroom. And when I say version 12, I mean after 11.0. So some of these things were in 11.1, some were in 11.2. Some of these things are new in 12, and some things are coming in 12.1. Okay, so as the vendor mentioned in the previous talk, we have these new equation manipulation functions. This, I believe, was new in 11.3. Add sides, subtract sides, multiply sides, divide sides. And for completeness, we also have this apply sides, which is a little bit different because if to actually make it like the others would be a much, much more difficult proposition. So at its simplest use, add sides and multiply sides, they're all pretty much the same. Add sides adds the same thing to both sides of an equation. Or if you want to combine two equations, you can give two equations and, in this case, subtract them. Now, you're not limited to two-sided equations. You can have three-sided equations, and it'll, then they need to, if you have two equations, they need to be the same length, because otherwise it's like, well, how am I supposed to make them match? And these functions are mathematically aware. So in this case, so both subtract sides and divide sides have a one-argument form, which the multiply sides and add sides don't have, which is move everything to the left-hand side. But it knows that you can't divide by 0, so the result is a over b equals 1 if b is not equal to 0, and otherwise it has to stay a equals b. But these functions don't just know about equations. I was worried this might happen, which is why, fortunately, I have this version, which should be here.
So what happened there? I've seen on one of the notebooks that I downloaded exactly the same.
So the short answer is we don't know, but I think it's trying to dynamically resize things to the screen, and it's getting stuck in that computation. So this is a simpler style sheet that doesn't try to be so clever, and so it also doesn't have this bug. Okay, and so, right, so we can support inequalities, and do I need to make this? Oh yeah, this is tiny on that screen. So that's the downside of the less intelligent. That looks like a good size. If people want me to make it bigger, just tell me. Right, so you can do inequalities. You can combine multiple types of relations. So here we're combining an equality and an inequality. And if you multiply an inequality by something symbolic as opposed to something concrete, it'll tell you, well, the result depends on the sign of the thing you multiplied by. Then we have apply sides, which allows you to apply arbitrary functions to, both sides of an equation or inequality. But this one is a purely sort of structural operation. So for example, if I apply sign to both sides of an inequality, well, depending on the value of the point, that may or may not still be a true result, as shown here. And that's just because for an arbitrary function, deriving the conditions, it's just not what is the purpose of this function. Okay, so that's some very basic algebra improvements. We've made a lot of improvements to limit. So those of you who are longtime users may know that limit used to give a one-sided limit by default. Now it gives a two-sided limit. And so this limit doesn't exist. You can ask for limits in other directions. So limit from above, limit from below, limit as you approach into complex plane, and the result is complex infinity. We also have new easy-to-remember values for direction. You might recall you had to guess whether +1 meant from above or from below and get it wrong at least half the time. So now we have from above, and it gives you the limit from above. And can you guess what its friend is? Well, I deliberately only typed half of it in to show you that it's a little small there, but you see that a bunch of completions came up from above, from below, complexes. Reals is the default. That means both-sided. You can also use the string two-sided, but we prefer reals. And so, we're giving you better help. We're giving you easier to remember names, and when you're trying to type them in, we're giving you better help about what you can type in anyway. And
what did the direction of limit lines in autocomplete?
Direction of limit?
Autocomplete at the bottom
Oh, that's a new feature where those are links to the documentation. So I will just make that reappear very quickly. So you may not be able to see, but it's a little book icon next to them. And so that's saying you're looking for direction, for values for direction, and you're inside of limit. And I have documentation pages for both of these symbols. So go straight to the help page for those functions.
From left should be there also.
What?
From left, from right.
No, I disagree. You can only have so many values. Certainly in a short list like that, you don't want too many. And I think from above and from below are pretty clear. I mean, we could maybe understand them.
First example, look at first example. Plus 0, and minus.
Right, well, that's from above.
But for example, for non-English native, that would be problematic. For example, in Spanish, we only use the equivalent from left, from right.
Okay.
Not that clear for non-English native.
Okay, well, then maybe we should add those as synonyms to the table. That's
I'll second the request or third.
okay.
English language, from
Okay.
the left, from the right.
All right. Well, we decided that from above and from below was more common in English. We had a fair discussion of this, but thank you.
We're not arguing for eliminating from above.
Yeah, right.
We want to keep them, but just add from the left and from the right.
Okay. Adam, you're a Polish speaker. Why didn't you tell us this? All right. Right. Limits of sequences. So this is so sometimes if you have the same expression, but depending on whether you're thinking of it as a function over the reals or a function over the integers, you get a different value for the limit. So here's sine of x pi and sine of n pi. And one doesn't have a limit as you go to infinity. The other is 0 because it's really a constant sequence. And similarly, here's -1 to the 2x and -1 to the 2n. And so we have a new special function, discrete limit, which is for computing limits of sequences. And it can be at either positive or negative infinity. I've just done positive infinity here. And not so much for your first 2 years of college, but we also have lim inf, and lim sup. So for -1 to the n, right, it's 1 and -1. And similarly for sine of n pi, sine of x pi, which doesn't have a limit, but obviously has a lim sup and lim inf. And since I'm a little bit behind where I want to be, I'll just go through this very quickly, but we also support now true multidimensional limits. So I'm taking the limit of this function as we approach the point 0, 0 from all directions. You can try, so this notation, point goes to point, or variables goes to point, means approach in all directions. This, one variable list of variable goes to point means take them in sequence. So limit as x goes to 0, then limit as x goes to y, you get 0. limit as y goes to 0, then x goes to 0, you get a different value. If you try to approach along the line x equals y, you get the third value. And so, we have one of these very singular points, and there is no limit. And using direction can be not just a single value, but a list of values. And so you can limit to half planes or quadrants, right? If you say both sided in x, but from above in y, etc., you can limit half planes, quadrants, etc. So documentation was rewritten to match the functionality, obviously. The details section has intuition building in illustrations, and here are some notable examples. So geometric limits is, so we compute here, and let me make this bigger so you might actually be able to see it. Right, so we compute the perimeter of a regular polygon. We take the limit of that as n goes to infinity. We get 2 pi r. We compute the area of the regular polygon. Again, take the limit. And here we have a nice illustration of what's happening. Limits as zooming. So here's another manipulate. Basically, as you zoom in, one function has a limit as you go to 0. The other is going crazy, so no limit. And sort of a very handy, right, we have sort of application examples which are, sort of inspired by things calculus students might have. So for example, we have a function. We want to find its domain. Okay, it's not defined at x equals 0. We take the limit as x goes to 0, so there's no limit. However, we have limits above and below, and so there's a jump discontinuity. And right, we have an example with a removable discontinuity, etc. And just since I mentioned them, here's the new details and options. So we show how to type this in. So now we have a limit operator that you can use so it looks more like your classroom notation. We have these illustrations trying to explain what's going on. And so maybe we need to expand this table to have from the left and from the right. An actual illustration to explain when you give it a numerical value, what that numerical value means, etc. Okay, so that's what I wanted to tell you about limit. Differentiation and integration. So we've added some features. You wouldn't think that at this point we would have a lot to add to D, but we found a couple. So we have symbolic order derivatives. So if you take ask for the nth derivative of x, it's x if n is 0, 1 if n is 1, and 0 if it's any higher derivative. And you might think the n equals 0 case is a little bit redundant, but it's really not, because if you say have a product and you need to take the nth order derivative of each side, then you need that base case in order for your resulting formula to be correct. Or the nth derivative of sine gives you this formula. You make a table for different values of n, and you see your nice cycle of 4 for derivatives of sine. We also have simpler results for certain important special functions. So here's Bessel J. You get 2 terms with a simple polynomial in front of the 2 bezels. And this is for the third order result. This is as opposed to a sum of 8. So in the old result, you'd have 2 to the n different Bessel functions running around that you'd have to sort of collect and simplify. And I just want to point out that we're not just simply applying the nth order result. We have a special technique for so-called holonomic functions to compute nice formulas directly, because we would have n terms if we had just applied as opposed to 2 terms. So we've strengthened indefinite integration. By popular demand, we now have constants of integration. So if you can say generated parameters goes to C, and you now, for your indefinite integral, get x cubed over 3 plus C. But of course, constants of integration sometimes aren't so constant. So if you take two integrals that in different variables, then you have an arbitrary function in one variable and an arbitrary function in the other variable, because when you then take the mixed partial, those will both disappear and you get back to the function you started with. And we, for completeness, extended this to the discrete integral, also known as sum, and also product. Whoops, so difference delta is the derivative for sum. Discrete ratio is the derivative for product. And notice how constants are generally flowing to the right for additive ones and to the left for multiplicative ones. We had a little issue in traditional form where the rules for trying to make nice polynomials interfered with that. That is fixed in 12.1, so they'll be at the end again, also in traditional form. New integration rules. So we've added some new integration rules for indefinite integrals. These are most noticeable in integrals with parameters in them, because integrate was already very strong in this. And there's something called the Ruby benchmark out there you might be familiar with. We can do essentially all the integrals on the Ruby benchmark now. So here's an example I actually managed to find of an integral without parameters that we can now do. But a more typical case of the kind of integral that you can now do, notice I have here an m to the power m. It's hard to come up with a closed formula for that. You can, but you need hypergeometric functions. So for any concrete m, integrate could do this. It's right, it's just a simple rational function. But for arbitrary m, we can now do that too. This was really a challenge, coming up with a sort of Calc 2 or a sort of integral that is now simpler because of our new rules. Yes?
In one of your results there, you have a root x cubed on the top and then x to the 3/2 on the bottom. Do you want to comment about that?
No. There might be a branch cut somewhere in there that is being avoided, but I'd have to think about it. So, I mean, you will find, so a lot of times a lot of the ones that we can do have fractional powers, and it's precisely because we can now do them because we have a formula that avoids the branch cut. So, right, so here's at least an integral that you might think a Calc 2 student might type in, and there's the result. They're supposed to know what an arctangent is. They may claim not to, but they should. And so you notice that one came back pretty instantly. This one was not so instant, and we have some elliptic f's and elliptic pies and whatnot. So this is definitely a nicer, simpler result for students. And like limit, we've rewritten the documentation. And so we have many more examples, again, many inspired by calculus texts. So I will just show you a couple of my favorites. So L'Hopital's rule. Right, so I guess I should point out, and again, it made it small. So right, so if you look at just our sections here, we have rates of change, implicit functions, optimization, L'Hopital's rule. So we have, a couple of functions. The limits are both 0. We can carefully check that the conditions for L'Hopital's rule, that it's not 0 in some neighborhood of the point of the punctured neighborhood, is satisfied. And so f prime and g prime are continuous, and g prime is not equal 0. So it's, we don't even really need to take the limit. We can just compute f prime of 0 over g prime of 0, and we have this pretty illustration of it. this regions of revolution. So this is on integrate. So we have, arc length, volume, regions of revolution, area between curves. So here's, pretty straightforward one. We have something rotated around the x-axis. We can just, we set up the integral, and we have a nice plot of, to visualize the surface. Fundamental theorem of calculus. So I won't go through this in detail, but I will sort of jump to the punchline of this example, that I have an f, I defined a g, and here I'm plotting g and f and sort of the difference quotient for g based at a particular point, and f, and you can move x around, and you can shrink h and sort of show intuitively the fundamental theorem of calculus. And so obviously this is a pretty complicated example, but my point is these are not just for the students. If you want to have a nice manipulate to show in class, instructors can steal these examples and make use of them. And I'll just show you one of these three examples. So I guess I should show you two. So this one isn't an example. This is the notes. We've sort of updated them to make clear sort of what it means, how you can type them in using sort of a partial derivative operator and sort of the different syntaxes. But also we sort of have examples of, for example, how to type in a template and fill it in order to type in an indefinite integral. Which leads naturally to my next slide, user interface enhancements. So we've long had this thing where when you type in two numbers in a row, there's a little gray times sign, so you're multiplying, that you have 2 times 3 and not 23 there. But we've generalized this to many more expressions. So if you have just arbitrary functions f and g multiplied, it'll show you that. And for example, if you're inside of a function and you forgot a semicolon, then having the little times at the end of the line to know, oh, I'm multiplying by the next line is really useful. On the other hand, we don't want it in between, 2 and sine and cosine. So that's in 12 already, this intelligent omission. In 12.1, we're improving the curation with giving the front end access to the kernel's list of mathematical functions. So, that should be better. We don't have a capacity for that yet. That has been requested, but it's not there yet. And then, so I will just show you one of these two examples, but you've always been able to, for long you've been able to get completions for letters, for special characters, but when you type in escape and start putting in a shortcut. But now we also have completions for what we call input aliases, which are sort of more generic things. So for example, we see here del dot, del x, del 2 give you little templates for a gradient, for a curl, or for a Laplacian. And so that's a nice usability enhancement. And syntax coloring, we've just as D and integrate and solve now have long sort of colored their variables, we've now made sure that find maximum and lots of other related functions also do this. Okay. I don't have really time to go into this, and I guess there will be a whole talk about special functions. So I'll just say we've sort of reviewed and updated 252 math functions. The discrete math team, which is a slightly separate team from us, is looking at 100 additional pages, which are more number theory or discrete math type functions. And this is an ongoing process ensuring sort of consistent presentation among different function groups. So all the trig functions have, you know, the same set of examples or possible issues, etc. And which of these do I have time for? So I will just mention we now have things like positive reals and negative reals, which format nicely with little tooltips, and we have input shortcuts. We have some formatting tweaks like conditional expression that Devendra mentioned. And there was a separate talk on sort of Euclidean geometry earlier, so I recommend you, if you didn't go to it, you can watch the video or download the slides from the Pathable website. So in conclusion, we've expanded capability, usability, and documentation with a view towards making Mathematica better for use in the classroom. We're still working on more, and feel free to get in touch. And any last minute quick questions before I hand things off to Adam.